in the middle of the course, so you will be able to understand all of it, but maybe some of it, and you can go back and you can search some keywords that you take away from here.
Maybe it is like gate key of your career. Maybe
Yeah.
you find another
Because
from here as well.
yeah,
I'm also a student, like we met a student here for attending a workshop.
so we will be starting soon. And this course is extremely popular. Like we had more than 600 people joining us, for this course since 3 weeks. Because these kind of courses, they are usually carried out through payment. So this is free of cost. You can come here for 1 hour. This is 1 hour lecture each day. So you can come here, join us in person. We also have some options of, doing it virtually on few of the days. So that's all about this course. Dr. Chinami?
We also have some practical session as well.
Hello, good afternoon, Professor Chen. Can you hear me? Professor Chen, you need to unmute your mic. Unmute your mic and also your video, your camera.
Okay, can you hear me now? Can you hear me now?
Hello, Professor. Can you hear us?
Yes, I can hear you. Can you hear me now? Can you hear me now? Can you hear me now? I can hear you. Can you hear me now?
Yes, I can hear you. Thank you very much, Professor, for joining us. Ladies and gentlemen, to our in-person participants and also to our virtual participants, welcome to OIC COMSTECH and Ningbo University Certificate Course on Applied Biomedical AI. This is day 13th of our day 12 of our 19 days long course on applied biomedical AI. And the title of our lecture today by Professor Dr. Chen is Recurrent Neural Networks and its Application. Professor Chen, I request you to please begin your lecture, and the floor is yours.
Okay, thank you. Okay, from previous lectures, actually, we specifically focused on CNN, image AI. Today, we are going to look at another application, major application of AI, which is the language. And in language, probably what you think of is either we have some kind of conversation, chatting with each other, or we have some reading task. We read some materials, either translate the material into another language, or actually try to understand the materials. So how can AI deal with this kind of language tasks? So today we are going to look at a simpler method, which is called RNN, recurrent neural network. Okay. Okay, so this is in big contrast to CNN. In CNN, we understand that it is some kind of focused learning of local features. In order to capture a local feature of in the image, we use some kind of filter to grab some important local features. Actually, we scan the image, the whole image, using a small matrix type of filter. and then to try to grab the so-called important ones. But in language, we no longer have this kind of local features because language is typically a long line of words from the beginning word and to the follow-up words. And these words typically have this front and forward, backward kind of relationships. So the question is, how can we grab the features of a language with this kind of front, forward, backward, this kind of relationships? So obviously, instead of scanning for local features, we need something that can actually scan from the beginning and then the next and the follow up until the end of some kind of sentences or groups of sentences, right? So that's why we have.
Professor Chen, I'm sorry to interrupt. We need to see your slides because we're unable to see your slides. Are you running your slides?
I think I did the sharing. Can you see it now?
Oh, yes, now we can see your slide.
Or maybe
Thank
it
you.
didn't. Okay. So maybe that's because of my mistake. So we actually uh, so this is the content of today's lecture. So we focus on a new method for it is in contrast to the image learning method, a new method for learning languages. So typically this is a RNN method, recursive, some kind of recursive type of process, reading from the beginning until the end. This kind of language process. Of course, in doing so, we may have run into problems if the sentence becomes longer and longer, and so that's why we have some variation of the RN architectures. Okay, so this is the slide I just talked about. So our new method is in contrast to the CN method. In CN, we have a filter that tries to capture, to grab the local feature of in the image, right? So that's the process, and we use this filter to scan the whole image and to grab any important feature that may be in any location. Maybe it is a flower, or maybe it's some kind of other object, right? But for language, and what we have is the some kind of front and back relationships between among the words in the beginning and the words that follow them up, right? So this kind of more or less like a forward backward series type of relationship or time dependent relationship, but obviously we need require a different approach. So we need something that can grab not only the local, of course, obviously local feature is still important, like a very important word, right? So that describes a important clue, right? But we also need to grab additional words that actually tells you the logical relationship, those kind of or evolution type of relationships. So obviously we needed this kind of approach that is different from CN, the grabbing the local feature. That means we need to have something that can grab the forward and the backward relationships. So in order to explain this new AI architecture, we take some simple examples. So this is a example of the activities we plan for the next day. So it obviously the activity depends on the weather. If the weather is good, and we may have certain activities If it is weather is not so desirable, we may have another activity, or even we just stay home, just sleep, right? But we don't want to be bored by by repeating the same activity every day. So that's why the activity of next day obviously should also be dependent or related to the activity of today. So if today is a party, maybe next day is not the party. So the weather-wise, it is it's equivalent to the local features, but activity-wise, if it is a previous activity, obviously it is a time dependent. So there's a relationship of today's activity and yesterday's activity. Of course, today's activity is also related to the local feature that is the weather. So we have this time series relationship as well as the local. So how can we do this? For the local, it is simple, right? It's just if we input the weather condition, if it is sunny, actually it leads to a activity time. If it is rainy, maybe it's a resting time, right? But what about the time dependent feature? So for this, actually, we need some neural network that can consider both the current conditions, the local conditions, and also the previous activity. So obviously, we need two inputs into our network, and then now our network should be selective on the activity, and that is dependent on the yesterday's activity. So this is a logical relationship we can first draw up so that we can understand or we can actually consider how we can build a neural network to achieve the same thing, right? So if yesterday's activity is some kind of running and today is sunny and we decided to do bicycling, if it is bicycling plus sunny, and we may decide swimming. If it is swimming plus sunny, then it is running. So we have this kind of scenario. Uh, Now we want to make it more complicated before we build such kind of neural network. So not only so this neural network actually plans activities not only for the next day, but it for quite a number of days, first, second, and so on and so forth. And also it depends on the local weather conditions and as well as the previous days activities. Okay, so suppose that we have already have the activity patterns of the last 5 days. So the question is, what would be the activity of the sixth day? So that's what the AI should be able to actually derive based on the activity patterns of the previous days. Okay, so that's the thing. Okay, so now we wish to design AI. So obviously, this AI must consider several factors. One factor is the current day. Right, so it depends on the current weather conditions, and then you have this kind of neural network. So remember that any neural network is some kind of weight multiplied by the current conditions. Okay, so what about the activities? So if we want to plan the activity of next day, suppose, so let's assume today is the first day, then obviously next day is the second day. So obviously we need some time dependent consideration based on the previous day's data, and then it should also have some weight, right? Some weight based on the previous day's activity. We use H. X is typically the feature of the current feature, right? So that's what we typically do. but H it may represent history. So it is the historical record of the event. Obviously, the historical record should have some weight in the determination, in the joint determination of the activity of the current day, right? Not only that, and we should also remember the activity. So if we go to the next day, third day, we not only need to know the activity of the second day, but also we need to remember the activity of first day, because we don't want it to so quickly repeat. So running, cycling, and then running again in the third day. Obviously, we want to have more variety of activities. So that means we have to memorize not only the immediate previous day's activity, but also the more previous ones. So obviously, it means that we have to have a series type of networks, not just one not just the two inputs, immediate history and the current condition. We need a series of network that can relay the historical influence of the previous day and then previous and the previous day. So that's something like that. And then our network should be able to give us the planned activity of the next day based on the records of the previous day. Okay. So in order to build such a historical arm of the network, obviously that arm should include the influence. So that means include the influence of the previous history as well as the current history, right? So it is a iterative kind of a process. And also it also includes the current condition of the current day. So something like that. And then okay, so now we can build some kind of network. So remember that our network, so it is illustrated here. Remember our network includes the information of the current day, day one, and then also from day one, we generate a history of the day one. And then that history should also be related to the next day. And the next day has another current conditions. And then the second day also creates a second history. And then that second history is related to the third one. Not only that, so the information should also include not only the immediate history, but also the previous history. So that's why there must be some complicated operations within this network A. So this is a unit of network. So remember that this unit not only has the capability of the input of the current condition, but also the previous history, actually related history, or something like that. And also, this unit A should be able to further relate the history to the next one, so on and so forth. So typically, this can be a very, suppose that we are dealing with a very long sentences. So this can be very, very long. So each unit only represents a single word. So if you have more than 100 or even more words, obviously this is too long. So that's why we use this simplified version to illustrate, because it is quite a kind of identical unit, and then you can have this kind of simplified representation of this long historically related network called RNN. So essentially, remember that we have this unit with the input of any current information, any xi, depending on how long this this series, time series or word series are. Okay, and also it has this kind of historical information. Historical information should be output and then input to the next next unit. So we can simplify it. Remember that this kind of historical information really it is a iterative process to many units. Just remember that. But we use this simplified version. Okay. So in reality, it's something like this. So every day, current information goes into the each unit, and also this unit actually combines the current and previous information, and then output and then input to the next unit as the historical record. Okay, something like that. Okay. So for the historical record, remember that we need to have the previous day's information somehow combined with current day's information, and then that information should be related to the follow-up units. So for instance, so suppose this is the first relay unit. It actually combines the information of the previous one with the current one. So the output actually includes the information of the previous one. And then once it inputs here, so it includes the information of the previous ones, and then it combines with the new one, and then it relays to the next one. So obviously, along this information relaying of historical record relaying process, obviously the historical record of the very early ones must still have some influence along this relaying processes. But obviously there's a downside because you combine the information of the historical record with the current information. No matter what kind of weight you use, obviously as this relay process goes for very long steps, very long iterations, the very early the influence of the very early steps actually becomes less and less. So this is the deficiency of RNN. So that means it cannot really deal with a very long sentences because there is this kind of information decay of the previous records. So only the very closely really, I mean the very close, very recent records, the historical records have more influence, are actually more preserved when it actually related to the next one. But very early ones actually becomes less important. Oh, okay, let's put that aside. We focus on the this RNN architecture. Remember that when you see this, you need to in your mind you need to have the concept of it is extended to actually many steps, iterative steps for this kind of historical plus current information reading, and also the current information must have many of them. So it is day by day, or it is word by word, and it is time series, second by second, T1, T2, T3, and so on and so forth. So just remember, whenever we deal with the RNN, it is some kind of a time series, or it is kind of a word series, and so on and so forth. Okay. Okay, so we can think of this kind of RNN structure. Remember that RNN structure is something goes horizontally, has many linked networks. remember that in CNN, we have many layers of networks. So it goes deeper and deeper. So actually, if you in CNN, actually, we go from left to right by actually learning more and more steps, and then until we have an output on the right? But in RNN, even though we also have a very long network steps horizontally, but that steps actually only try to learn the relationships of a time series or relationship of word series. But the output
Professor, we are unable to listen you.
Yes,
can you hear me now? Can you hear me now?
Yes, Professor, we are clear.
I think our network is down. I'm using my hand phone to for this. I don't know why the network it's the Wi-Fi seem to be down. So there are
Yes.
some kind of problems. So sorry for about that. I think maybe our network has some kind of a problems. Okay, we try to complete because my handphone may not have enough battery, so I try to hang on. Okay, so anyway, so this is the mathematics of the formulation. So essentially, remember that we must have some kind of historical record of the current or the new state, and then we have the record of the previous state. It is in an iteration process, so it can relay. And then we have some kind of function acts as the weight. So the function actually consider the weights.
Professor,
So yes,
sorry
can
for
you hear me?
disturbing. Sir, we are not sharing the, here's a not showing the lecture slides.
Oh, okay. I thought I made the
It's
sharing. How come I don't know why it is not working?
not,
So this is the second time.
yes, now it's
Uh,
showing. Thank you.
So it's the second time because I already made the sharing just maybe 1 or 2 minutes ago. I don't know why it happened this, again. Okay, so this is the mathematical function for the relationship. So the f x as a kind of nonlinear weights not only consider the historical part but also the current information part or something like that. Okay. Because we have two components, so this kind of weighting must consider both. So we have the current. Sorry, we need to make the laser point. Okay, so we have the current. Current information, we have the historical information, and so there's this kind of matrix operation to consider the weights, so that we can cover the weights of both. Okay, so now we can construct a simple RNN. Remember that we have the weights from the historical part, we have the weights from the current information part, and then we somehow join them together under a matrix operation, and then that kind of information is related to the follow-up unit. So you will have this kind of a series, right? So we have this kind of series. So regarding to the operations, there must be some definition of the symbols. So it is listed here. So the block is a network, and then so you have this kind of, depending on how you join, add up or join the information together, there's this concatenate operation. There's this kind of simple copy operation, or it just goes straight forward operations. So that's this kind of operations, and also even the nodes have some kind of definition depending on the this is a nonlinear function. There's some other operations for the state and for the input and so on and so forth. Okay. And also, depending on the task, and our neural network can be of different forms. So remember that the input is always from the bottom, the output is always on the top. So if it is one input, one output is a simple, no matter what kind of network, whether it is wide, fatty or not, it is very similar to a CN. So only the difference is in the architecture. So this is what we are familiar with the classification model. Suppose we could also have something that we input a single unit of the information, like an image, a vector of from an image, and then we have a time series or word series of output. So it is one to many, essentially one input and many output. So this is good for image caption. In image caption, we have one image as input, but we have many words as the caption. as the output. So each word actually is represented by one unit. So you have more. Alternatively, we could have more words, more input with many input with a single output. So this can be the sentiment, meaning that we give you some sentences and then you output some kind of image to describe what the sense or the some kind of essentially some kind of scope of the sentences you described. Or else we could have many to many, many input, many output, and then they are not exactly corresponding to each other. That means it's not one input and then through the network you have output, but rather this kind of thing. So this is more like a sequence to sequence language translation, those kind of things. But you could also have this kind of relationship fixed. So you have one input unit and you have another input unit, but you allow somehow the first input, the historical information of the first input to influence the second output, and so on and so forth. So you have this kind of, so this is called so this is also many to many, but it's different from the previous one. So it's called it is more useful for some kind of biological sequence analysis, mutational effect, and so on and so forth. This kind of thing. Okay, so for many to one, many input, one output. So this is the typical architecture, for the algorithm. For one to many, this is the typical architecture, and then many to many, one to many, and so on, so forth. So this is the kind of things. We could also, so remember that we need to combine the information of historical part and also the current the data part, right? So the combination could be just like this, a simple combination, and along with some kind of nonlinear operation to actually dissect, to actually digest the combined information. But what about, so remember that, need to put this outside. Remember that even though we have this kind of long time series or word series, right? But the input output is always bottom to the top. So essentially, no matter how long the sentence is, actually the information processed is just a kind of a single layer process. What about we make it deeper, just like a scene, right? We add more layers to learn deeper and deeper knowledge embedded or contained in a language or in a time series. We could do that by adding another layer. Just like a scene, we add another layer. So we could have actually a multi-layer RNN. But remember that we in a single layer RNN is already quite a quite a number of networks. If you have more layers of RNN, multiple layers of RNN, you actually increase the computational load very quickly. So that's why you rarely see a multi-layer RNN precisely because of the need of more computing power. But it is no longer a problem in recent years. But again, you still, even though the computing power is no longer a problem, but the RN becomes a problem. Remember that I mentioned that it quickly forget the knowledge of the previous ones. So that's the problem. Okay. With this kind of multi-layer RN models, so remember that historical information goes from the left to the right. So it is one directional, even though the other information goes from bottom to the top. You could make it the information not only goes from left to right, but you could also make it from right to the left. Why not? So that means the information doesn't have to be only in one direction. So you can make it in the opposite direction. You can also make it bidirectional. Bidirectional. Moreover, your network, just like CNN, right? So the different layer of the network doesn't have to have equal number of nodes or equal number of filters. So you can have different number of nodes, just like, and typically you want the nodes of the deeper layers to have a fewer number of nodes, so it becomes a pyramid type of RNA. So if you see some pyramid RNA, you immediately know it must be this kind of structure. That means the information or the data processed in the previous few nodes actually are combined into one node to have this combined information. So you see this kind of networks. Okay. So that's another problem here. So remember that if the networks becomes very, very long time series and some information is forgotten, right? And also if it goes upwards with many, many nodes, you can see that information is even becomes even further messy because we know that logically in the long sentence the first few words is still very influential even until the end of the some short story, right? So how do we deal with this kind of situation? Obviously, this kind of simple joining of the historical and the current information, this type of architecture is no longer the choice. So that's why we need to introduce a more complex network architecture. I think it's blocked. I need to. How come I cannot remove it? Okay. So this architecture is called LSTM, long short. This kind of not only it has the short memory, but it should also have long memory. This kind of long short time memory. This kind of network on the bottom part. So the top part is just a typical scene, a simple journey. So how do we have this long memory? We know that if we can easily get a long memory if we allow the information of the first node, or the first time, to go straight without any interference, go straight to the next one, and then go straight. If it is a straight type of information, we know that it can actually be memorized for as long as you like, if there's no other influence. But if we also want to have a short memory, then we can have the bottom one, and then we have a short memory, and then we have essentially two historical information now. One is the long memory information, the other is the short one. A short one only kept for the recent ones. But we don't want this long time series to just go without some kind of essentially some kind of processing. Because if we just keep straightforward, and then for the next one we still have another feed keep the information forward, then you are going to have too many earlier historical ones. It is too computationally costly. So that's why we still have a compromise of the long historical event, but somehow with the current event joining the long event, and then it goes so that uh, we still keep the joining the information of the first time one, time two, T1, T2, T3, but somehow we try to make the decay of T1, T2, T3 to be slow, very slow. So that's why we have this very complicated networks. So it has this kind of complicated operations to try to have some kind of information joining the time one, time two information, join the time two, and then join the time three, and so on and so forth. So this kind of architecture. Okay, so in order to have this, so there must be mathematical formula to try to get the information. So that's why there are many different type of processing. For instance, this first one is called forget gate because it decides what information is supposed to keep, what information is supposed to be discard, to throw away. Anyway, so this is about the mathematics, and you just accept that. So this is the operation of the forget gate. So it actually decide what information can go through to the long historical record arm. Okay, and then there are some a few other gates like this operation. And then and also this operation to have this complicated information. I will not go into the details. Only if you are interested in RNN algorithms, and you can actually read some textbooks, read some internet records. But anyway, we just accept that mathematicians, statisticians, they already figures the things out to help us to determine what the information is supposed to be thrown away, what information is supposed to be joined into this long historical arm by this kind of proper complicated proper operation. So we just accept that they have this kind of operations for us. So essentially, this is the actual network. So you can see there are many different steps in order to have this information sent to the long arm. Okay, so you can see that LSTM is not a easy operation. It's actually very complicated operations. Okay. So we accept this, and then now we want to compare the difference between RNN and LSTM. Remember that LSTM must have two arms now, not just one historical arm. It has a long historical record arm, and of course both should still have this current condition input. So it has and also inside this box there are more complicated multiple operations to actually to filter what kind of information should goes to the in what form it should go to the long arm, and then each should have this output on the top. So that's the differences. Okay. Now we look at the application. So here we actually don't distinguish a simple RNA and LSTM. We assume LSTM is just some more complicated form of RNA. Now we look at the application of RNA. So one application is machine translation. So remember that the input is always in the bottom and the output is on the top. So we input a sentence in a language, and then we output the sentence in another language. Obviously, this is a many to many, and also because there's no one-to-one correspondence of the first word with of one language with the first word of another language. Even the number of words could be different. So that's why we should have this kind of architecture for this machine translation. So this is because the word should have the first to the last word. This kind of logical type of relationship. So the output should also have this kind of logical relationship, and then we could so depending on how long the sentences you allow, typically you may need to use LSTM rather than a simple RNN. Okay, so that's the process. Okay. Next application is the chat, language chatting. For a chatting mode, typically we have some kind of input, and then so essentially we input, for instance, we input a question, we expect an answer, right? We input some kind of first part of a conversation. You must have a follow-up conversation. This type of sequence to sequence chat mode, because chatting actually chatting actually the logical relationship goes not only for the input sentence, but also it continues to the output sentence. So it is a very, very long. So essentially, the logic goes very, very long from the input sentence to the output sentence. So you must typically use a LSTM. So of course, LSTM, the first part is the input part, so it's the encoding part, and then the output part is the decoding part. So for the encoder, decoder, and we may revisit it later on, but not here. So anyway, so a chat model, RNN model should be, or LSTM, specifically our LSTM model must be quite complicated in order to be able to actually make the chatting sensible, make to have it makes should to have sense of to the human knowledge. So these kind of things. Okay. So the next application is a speech recognition. In speech recognition, so just like me, I'm speaking now, and then the machine should be able to to receive the voice. Essentially, these are sound wave input, but output the sentences in words. So this must be so this is the typical network. So this is a typical network. So obviously the voice and then the output has this kind of almost one-on-one relationship. That means the first voice should correspond to the first part of the word, the words, right? The sentences. So that's why you can use this kind of many to many networks. because it makes it simpler. You don't have to have too long, very fat, very wide network. But you do have you do need multi-layers. So multi-layers because we know that some different people may have different accent. So that's why you need this kind of very deep network in order to be able to understand the speech. So this kind of process. The next application is this image caption. Image caption meaning that we input an image and then we output the caption sentences and the words, those kind of things, like these examples. So this network, obviously, it is one. So essentially, words actually contains multiple. Essentially, it requires multiple units, right? And then the image, depending on what is the image task. For instance, if we do this image tagging, that means we need to have the multiple words. Each word describes one of the objects in the image. So that means the input of the image objects are the input into the network and then into the RNA network. But you have multiple objects, so that's why you need this first a scene to have this object recognition, and each object is inputted as one unit into the RNA. So you still have this many to many type of networks input into the system. Okay. And another is this image tagging. Image tagging. So for image tagging, so essentially it actually it first it identifies the object within the image, and then it somehow tag it with this kind of operations, because tagging requires of the essentially a conversion of the object, the object, essentially the pixel features into the word features. So it still requires this kind of RNN operations. So typically, what you can do is that you have a scene operation to output objects one by one, and then you can input the object, and then train a RNN neural network to output the descriptions of the objects. So depending on how, so you have one input of the whole image, and then it recognizes how many objects, and then depending on maximum number of objects, and then you have a maximum number of RNN nodes here, and then each describes a particular object. Okay. So these are the applications. Okay, so maybe I just stop here because I'm concerned with because I didn't bring another charger to charge my phone. Okay, so okay, let me just stop here. So now it's a question time. Do you have any questions?
Okay, thank you, Professor. Let me ask from physical participants. Do you have any question? Any question? Any practical related questions? In a past lecture questions? No? Okay, let me check
No.
it in a question answer sessions online. Uh, कहाँ चले गए? Question answer. तीन question का थोड़ा सा
उसके अंदर ये देखिए कोई है उसमें जब क्वेश्चन आप टाइप करके उसमें वही
Any questions? Oh.
Sir, let me check it online. Okay, the one question is by Samyuddin Shinwari, and he's asking how to vanish gradient problem in RNN.
It is a good question. So, essentially, so this is the reason. So typically, RNN works for short sentences, and so the gradient problem is not that serious. But you have a very long sentences, and it requires you essentially, I think it's a kind of, you have to modify the network to somehow have the information jump into the some region. But if you do that, it's not too far away from the transformer architectures, which is the topic of the follow-up lecture. Okay, essentially.
Okay, thank you. The next question is by Rajab, and he's saying, what is the complexity of training and deploying CNN and RNN?
CNN typically you may need a very deep CNN model, meaning that you need to have many layers. So the more layers, it means more parameters, right? For RNN, so typically it has a few layers, one layer or two layers, but it is if you deal with a very long sentences, or if you have an image of many objects, obviously you need more nodes and then if we use this LSTM architecture of RNN, you know that the network is actually quite complicated, so it is still time costly. So that's why people actually totally abandoned RNN, jumped to transformer, but a transformer has even more complex architecture. So that's why it requires even more data. Fortunately, for both image and the language data, actually, people are not short of the data, particularly it is for daily chatting, daily image tasks, that's okay. Only if it is for some specialized fields, you have a few data, and then you need to worry about the problem. Okay.
Okay, Professor, the last question is by Samyuddin, and he's asking, there is a vanishing gradient problem in RNN by V vanish through input output for get gates in LSTM, how the gates work.
So it concerns with the complicated mathematics, and because essentially depends on the data, depends on the signals, and then you can have some, for instance, you have mathematical operations for example, you may have you remember mathematically you have this Fourier transform, Fourier series, you have this Taylor series, and then you can keep the most important terms, and then throw away the other terms. So I just give you this kind of illustrative examples. Of course, for time series, it may not be this simple Fourier transform form. It may be other forms. So that's why it is quite complicated. That's why I try not to get into details. Okay.
Okay, thank you, Professor. The students asked for your slides.
So the slide is not in the website. I thought I gave all the slides. It's not on the website. Or if not, I can resend the slide to you. Okay.
Okay. Thank you, Professor. That's all for the day.
Okay.
Hope see you soon tomorrow, inshallah.
Okay. Okay.
Bye bye.
Okay.
Bye bye.
Bye bye. Bye bye.